All right, today we're delighted to have Professor Silviana Amethyst here from the University of Wisconsin at Eau Claire to talk about, appropriately for Halloween, skeletons of algebraic curves. Thanks for being here.
Thank you. And thank you to the math faculty of Exeter for having me out here. It's really good to spend some time with Diana and learn about your campus. I've been inspired this morning in the time that I've spent in your classrooms, and I have concrete things that I've written down that I'd like to do in my own classrooms at UWEC. So in preparation for this talk, I've thought about what to talk about, what I thought would be fun and interesting for a variety of mathematicians and teachers and students. And on account of it being a Halloween, and I love Halloween, I was like skeletons, because skeletons are kind of spooky. And so I figured I'd tell you about skeletons of algebraic curves. So I just want to talk about, algebraic curves. And my objective is to fill the 2 boards by the time that I am done. The expected duration of this is somewhere around 40 minutes with an invitation to ask questions throughout at any point. So I'd like to just first talk about what an implicit plane curve is. So when I say an algebraic curve, I mean that I'm working in the world of implicitly given expressions between multiple variables. And so I'm thinking about something that looks like f of x, y equals 0. And everything that I'm going to talk about today is readily generalizable to higher dimensions, but the pictures that I'm going to draw work much better in the world of planes. And so I'm going to put planes right here for several reasons, for drawing, as well as one of the first pictures that I'm going to draw. I'm going to use Desmos. Well, I used Desmos already for it. So when I say f of x, y equals 0, there's a really special relationship between x, y, and some special number 0, right? Like if I just choose some like random x, y and plug them into some function f, I probably don't expect to get 0 unless I just happen to have the 0 function, but the 0 function is not interesting. So why would I be thinking about that? So what I really mean using set builder notation is the set of points in the plane such that when I take x and y and I run them through my function f, I get 0. So this is just really shorthand for this. And now we can ask ourselves, well, like, what does something like this look like? And I have an example. And it's one that I used the other day in a set of problems on implicit differentiation in my Calculus 1 class. And so if I have something that looks like y to the 4th plus xy, and then I want that to be equal to x cubed minus x plus 2, that describes a really special set of points in the plane, and not particularly special because there's nothing special about this relationship. Maybe it's special because they're all like low integers. But if I run this through Desmos and I just type this expression in, it will give me the following graph. It's going slightly down right there, and then it goes off to infinity off in that direction. It's coming off from infinity down right here, and then it's horizontal at that intercept, and then it loops back on itself like this. So there's a decent representation of this. So a point on my curve right here is a point xy, and it has to satisfy the relationship that when I take the y coordinate quad it, and then run the rest of it through this, these two things happen to be equal to each other. And now you're like, but you told me equals 0. And I'm like, okay, I'm down with 0, no problem. We can just move everything on the right hand side to the left hand side, and now I get a 0 equality relationship to exploit. So I'm going to be doing equals 0 through everything, and if I ever write a function down, I'm probably setting it equal to 0 and solving. Everything's equal to 0, and if it's not, take whatever's on the other side and move it to the other side. Now it's equal to 0. That gives some convenient notation. So I just drew down a curve right here, and there are such things on this as lines that happen to be tangent to it. I can easily draw a tangent line to the curve, and I could draw a tangent line down here, and we should be somewhat uneasy working with something that looks like this because it's not a function. And so if I want to like differentiate to find the slope of the tangent line, and I care about slopes of tangent lines because they represent instantaneous rates of change, then like, what am I supposed to do? Like there's no like y equals f of x. They're all mixed up together and I can't isolate y. And if by some trick you can't isolate y, congratulations, let me just add some additional terms here and now I'll make it impossible for you to isolate y on one side of it. So
It's a little surprising there's only one branch.
I think it depends on how you look at it, how many branches
Okay.
that there are. So do you mean that I only have to like branch once?
Well,
What do you mean?
it's a fourth degree equation in y, right?
Mhm.
So, I would expect generically for solutions.
Yeah.
Which tells me, I can also combine that with whatever the algebraic properties of that cubic are. It's gotta have more than just one branch, but maybe not.
There might be some stuff that lives in the complex world, because over in the complex
Sure.
coordinates, we certainly have four. That
Sure.
much is certain.
Sure.
And also this is through Desmos, and Desmos makes mistakes, and it'll point out a mistake that Desmos makes on another curve I'm gonna write in just a little bit here. So Desmos might be wrong, right? There might be additional stuff here that Desmos
Yeah.
can't see.
It's just doing a gradient hunt, I presume, starting from,
Exactly. So I think what you mean gradient hunt is it's looking maybe it's splitting the plane into like a region of positive and negative, and it's going to find where it changes from positive to negative. So that's one example of what I think I'm starting to get at here, which is like, what does it mean to compute this curve, right? What do we mean to compute an object or to represent an object? And I think that's my fundamental question that I'm trying to get at today is, what does it mean to compute a curve? That's my big driving question. What does it mean to compute a curve? And we could practice implicit plotting like Desmos is doing. I can't read their code. If they supplied me their code, I'm pretty sure I could read it. I'm pretty sure what they're doing is that they're taking a left-hand side here and they're detecting sign changes. And there's some like sampling of the plane. And then they're going to do like interpolation to draw something smooth across that because they gave me something blocky probably. Maybe they're doing something even fancier than that, but I doubt it. And I have evidence that they're not doing something fancier if we try different curves. So what does it mean to compute a curve? In the world of Desmos, it means give a picture. And furthermore, they have a picture such that I can select a point and they'll actually tell me coordinates on it. And I have ideas about how they're doing that as well, probably involving Newton's method, but I don't know. I haven't read their code. This is not what I think of when I mean to plot a curve, but I do mean the branching. I want to talk about that branching because though this thing does in fact fail the vertical line test in the sense that it's not a function, if I were to zoom in on a piece of the curve, we know that this thing is, let's see how decently I can do it. Locally, if I just look at a piece of it, it is most certainly a function, right? So locally it's one-dimensional, which means that I can represent it as a one-dimensional object. So it fails the vertical line test. I can locally look at it as a function, which means that I can compute like a set of functions maybe that represent this object. And so let me highlight one way that I think that we would do that. I think I would take a line down here, maybe take the x-axis, and its vertical translation doesn't matter. I'm going to do it separate down here. And if I do this, then if I try to take, given an x, compute a y, I need to be able to compute two different things. There's going to be a piece on the top, right? I have a branch on the top, and then I would have a branch on the bottom. I can compute two pieces, and there's this really special point right here that I need to know something of, right? I need to know something about this. So I need to be able to compute points like this one right here, because it's where I would switch the branches. Or maybe if we're not thinking about switching, it's where two branches come together. Or another way of thinking about it would be to think about if I look at what's happening above a given x value, there's like no curve, and then all of a sudden there's some curve, right? And then every time that branches come together or split apart, I'll encounter another change like that. So I want to be able to identify points like this, and I'm going to identify these with the word critical point. So that is what I'm going to call a critical point. And that sets the tone for what I'm going to talk about for the remainder of my time with you today. So I'd like to return to a more familiar situation, which is that of a circle. Because like we should start simple, should start simple. choosing a circle because I believe that we've all done this at some point in our lives, for everyone in this room, and probably most people who would watch this recording later. So a circle can be given by something that looks like this. This is the set of x and y such that x squared plus y squared minus r squared equals 0, always equals 0. And the canonical way to parameterize this object is to cut it horizontally. So that's my x-axis. And if I happen to solve for x in this expression, or solve for y in this expression right here, I can find that y is equal to the square root of r squared minus x squared. And that gives me a y. So that if I have an input x, then I go up and I find my point y equals the square root of r squared minus x squared. And the branching, of course, yeah, comes from the fact that now I have 2 copies and I have to account for that. This is why, like we have essentially a double cover. Square rooting gives us 2 things. So I need a /PM right there in order to give me my plus or minus. Okay, so if I think about this as being a space, what I'm really doing is I'm looking in the direction vertically and I'm asking, where does the number of points change? And we're going to find these 2 points right here. Right, we're going to find those 2 points. And there's nothing particularly special about the x-axis. So I could also take a line like this and parameterize the curve like this. My equation is going to change if I want to represent this in terms of some coordinate, which I'm going to call P for projection. And I will pick out the points out here. And I can choose any line I wish. I want to consider a slight change to my system in order to think about a possible issue that might happen. What if, right, that's the mathematician asks the question, what if? What if I just multiply this expression by x like that? What does it introduce to my object? How have I changed my object?
Y-axis, yeah.
Right, because now I have 2 different ways that this left-hand side could be 0. I know that if the product of 2 things is 0, at least one of those 2 things is 0. We already know that x squared plus y squared minus r squared gives me a circle. So if that's not 0, then well, x must be 0. And if x is 0, then this whole left side here is annihilated and y is a free variable. So I would end up with a vertical line. And this is the picture that Desmos will give me if I input this expression. I tested it this morning. I was like, what is Desmos? Desmos gives me this.
It doesn't go all the way up?
That's correct. Here is the first error that Desmos makes when working with implicit functions. It does not recognize that this line goes to infinity. So there's something wrong with this gradient hunting algorithm that you refer to, with doing the sign change, with like discretizing the plane and hunting for sign changes and then interpolating.
Stopping at the singular point, threefold at the top.
Oh, yeah, there's singular points right here.
Yeah.
Yeah. Okay. So one thing that I think it's important to think about here then are those singular points at the top and the bottom, and that's, I think, one of the directions I was going to go in my talk right now. So I need to know something about these points, right? I need to be able to compute not only my side, I need to be able to compute not only my critical points, but also these singular points, because they are also critical points. So critical points come from looking at where the number of solutions above you in the implicit function theorem or in that parameterization changes. And I would go from 0 to 2, and then all of a sudden to 3, and then 3, 3, 3, until I get to 2, and then to 0 again. So these show up, and my algorithm will come back and deal with the fact that that goes off to infinity.
Can I ask what is a P is? I forgot.
P is a coordinate on this copy of the real number line. So this is the x-axis, this is the y-axis. I'm just going to call this the p-axis. It's just an axis.
Why we need P?
That's a good question. Why do we need P? What do I do with this? How does understanding this line right here give me tools to gather information to compute this curve? So what I'm going to do is I'm going to consider then, we're not doing that direction. We are doing this direction right here, and I'm going to call this direction pi for projection, so that I get P coordinates by having computed pi. And I'm going to think of this as a function of x and y. And if I take a point on my curve, anywhere on my curve or anywhere in the plane, really, I can feed any points I want through it. It's going to give me coordinates on this line right here. So this is a method of linear projection onto this. And I can think of that equivalently as pi sub x comma pi sub y. So that gives me a way of projecting onto this.
Pi x, pi y is the point on this line.
Yeah, and so if I take pi x y, that's pi x times x plus pi y times y. So what I'm going to do is I'm just going to take my xy coordinates and I'm going to run them through this linear function right here, and it's going to give me coordinates on this line. So I'm just projecting the object onto this line. So there's kind of a signature now in terms of how my curve projects onto the space where there's like zeroness out here. There's two-ness in here. I have three-ness, two-ness, and zero-ness.
If your line is supposed to be infinite, then.
Oh, I guess it's oneness out there.
Then wouldn't it go from 2 to 2 at your critical point? Or 3 to 3?
Yeah, it would. It would.
It would.
Sorry, I got misled by decimal.
Yeah, seriously.
There we go. 1.
So it goes, but so then I guess I was
It does.
thinking like it actually, in the case of these numbers, this then isn't, it goes from 3 to 3.
It
Goes in and.
here it goes 3 to 3. Here I have 1 to 3.
Yeah.
3 to 3. And for just a moment, there's 3 things coming together. So there is a drop here. So even though it's not
okay.
changing across this, I do need to witness this point right here.
Because it's like 2 for a second, is that right?
It's true for just a second. Yeah, for just that 1 second, right? Yeah. So what's my tool for getting a hold of these things? Well, think about this special relationship between this vector here, this direction vector, and the curve. If I just translate that vector over, we can see that the tangent to the curve is parallel to the direction of projection at these points. And then it's like, well, what about these spaces here? And at these singular points, I would say that there is no tangent at these 2 places right here. We can detect these algebraically. I think of myself as a numerical algebraic geometer, right? Here's the algebra and here's the geometry, and I love it when they're both present on the board. So if I want to compute these points, I need to find where this vector is parallel to the tangent to the curve. And I can do that with relative ease by forming the following system. What I'm going to do is I'm going to take f of x and y. There's going to be equal to 0. Here's the system right here. And now I need another equation to pick out these points right here. I know that the tangent vector to any point on this is a vector f sub x comma f sub y, where I'm using the subscript notation to indicate that I'm taking partial derivatives in those 2 directions. So this is df dx comma df dy. So I have this vector right here, and I'm going to inner product that with actually the vector that's perpendicular to this. So the perpendicular vector is minus pi y comma pi x. And I'm going to inner product these 2 things together right here. And I want,
Is that same as dot product?
yeah, dot product. So I get another quick,
I'm sorry, I was just gonna alternatively, the derivative vector is a row vector, and then the that sort of perpendicular is a column vector.
Yeah. I love how many ways there are to think about these things. It's one of the things that I think is glorious about mathematics. So what I'm going to do is I'm just going to take the orthogonal vector out here to the direction of projection and inner product it or dot product it with my tangent vector, and I'm going to get pi sub y times f sub x minus pi sub x times f sub y. And now I've arrived at a point of bad notation. There's much of that in mathematics where I'm using subscripts to mean different things here. So I probably should go back and change these to be like 1s and 2s so that I know that they're like indices of things in a vector, not partial derivatives. But there's some equivalents that I really do get to think of these as partial derivatives, because these are partial derivatives of the pi function with respect to those variables. So it's an abusive notation, but I think it's a valid one. And if we solve this, I will in fact get these points here, my critical points, my genuine critical points, which I distinguish from my singular points. For my singular points are the ones that are going to show up as solutions to the system regardless of my coordinates that I chose, the numbers that I chose for my direction pi, right? Because at my singular points, at these points right here, what characterizes those as being singular is that the derivative is zero there in all of the variables. There is no well-established direction of tangency. The tangent vector is essentially zero there. That's why I'm like kind of dead in the water. So at my singular points, and I think I should write this down. So at my singular points, which I abbreviate as sing, at singular points, I know that f sub x equals f sub y equals 0. And so regardless of the choices of pi, this bottom equation vanishes and the top one vanishes by virtue of having been on the system. So solving the system right here gives me a tool to compute not only my critical points, but also the singular points. And once I have those, I'm pretty much scot-free because now we've described the places where everything's interesting. Yeah, what's up?
So when you wrote it in that way, as you said, now this sort of the pi vector and the f vector, or the pi derivative vector and the f derivative vector are both row vectors. So should I think of this as taking now a determinant? As
Yeah.
a two-row vector? Okay.
Yeah, I have written down in my notes attached slides to make for this. So there's an equivalent formulation of this, which is actually what I use in the software that I wrote. Because remember, this works in any number of variables. So there's some like f of x, y, z. There's actually multiple f's. So I can't just enter product right here. So the equivalent way of formulating this system, which is I think more correct, is in terms of determinants, which would be to take the system f of x, y, and I want the determinant of f sub x, f sub y, pi sub x, pi sub y itself to be 0. And a note for those who are thinking about like how to actually solve these things. Maybe you're thinking about how would I like use software to compute the solutions to this. Determinants are scary because I'm going to take these are polynomials, or at least these two pieces right here are polynomials. So the degree goes up, especially if I have more variables than just x, y. This right here is a whole is almost a square matrix minus one row. I have the completing row to get a square matrix such that I can actually compute the determinant. So this determinant operation produces high degree polynomials, which are scary. So we should actually do this by computing like left or right null vectors, because then I don't get high degree terms.
Can I ask a more mundane question, Karen?
Please, Gwen.
I don't see f sub x, f sub y equals 0. Are we talking about f that has x times x squared plus y squared minus r squared equals 0?
So f is just the left-hand side of this expression right here. So f would be x times x squared plus y squared minus r squared equals 0. It's the whole product.
And both of those derivatives are 0 at the top of that circle?
Yep.
So, yeah, for that
Can we see why
polynomial,
fy is fx, isn't it
Right. fx is
going to left?
non-zero, but fortunately the projection derivative is 0.
Okay, so fx equals fy equals 0 isn't exactly what we're looking for?
This is,
It's just these 2
things
points.
going on.
Yeah, that's just these 2 points. And we can see it. So like if we take, let's just take this expression right here. So I have x times x squared plus y squared minus r squared, just as a function. Let's forget the equal 0 part for a while.
So this is f of xy.
Yeah, this is f of xy. Yeah, so there's f of xy, and if y happens to be, sorry, if x happens to be 0,
What's the pi in our example?
So you're talking about the critical points of z equals f of xy.
Yeah.
Okay.
That's, yeah.
I don't often
Down
think
here.
about it like that, but that's another valid way of thinking about it.
if x equals 0, then I say constant multiply by everything. So,
Then I get 0 equals 0.
yeah,
Right.
yeah.
It
You
seems
take
like,
the partial with respect to y. X is
And then you
constant,
said x equals
then you
0,
said-
yeah, okay, I see now.
Okay.
Alright, I got it,
Yeah, I think I wasn't prepared to just like do that differentiation, but well,
it's fine, I understand, I'm sorry.
no, thank you so much for asking. I don't need to apologize whatsoever.
so the multiplicities of the 0 for that, I think the determinant's equal to 0, right? Oh, that's the other equal.
The multiplicity
You're
of
you're
what?
building a set of equations that are equal to 0. I
Yes.
guess, right? So the multiplicity of the roots then should distinguish between that awkward, right? The three folds and then just the ordinary critical points that get projected to zero.
That's right. There's an unfortunate confounding factor, which it's possible to have singular points of multiplicity 1, which is something that took me like 2 years after I wrote software to do this, to actually see that happens, that you can have singular points of multiplicity. So you can't just look at the multiplicity. If the multiplicity is not 1, because we'll get a one-fold cover of these when I compute solutions to this and a multi-fold cover of these when I compute them. But it's possible my singular points are also of multiplicity 1, in which case I have to do something else. And what we generally do is like compute the rank of this matrix. And that's a better indicator. Yeah. Thank you for your astute observations. The point of this, my friends, is that I can compute all of the interesting places. And aside from these 4 points that I've computed right here, everything else is pretty smooth, like it's good, right? I have like an arc right here, I've got some line pieces outside here, I've got an arc right here, a couple smaller arcs. We've pretty much fully described this in a sense. I mean, if all I have is the picture of those points, which I'm going to replicate over here in the space that I've left for myself to do 6 steps. Because I think about the algorithm to compute the skeleton of a curve in 6 steps. So I'm going to step over to the right.
Ta-da!
So let's see if I can replicate my picture. I now know that I have, let's see here, I'm going to put stars at my singular points because it's easy to lose track of which ones are supposed to be which. I have a copy of R that I'm projecting onto, and I happen to know these things. So I'm going to call this the critical points. And as a subset of those, I get the singular points. It's not particularly useful in the case of curves to distinguish between them, but it is if I do surfaces, which I'm not going to talk about today. Okay, so step 1 is the critical points. And something that I think should next give us trouble is this region out here, because I haven't like given a way to get a hold of how this thing is going off to infinity, right? Like if all I have are these 4 points, how am I to tell that there's an additional piece out here? Like before I go any further, like I need to know that something out here is happening. I know interesting stuff in here is, but I need to know something out here. What do you think? Do you have any ideas for what I might do to figure out what's happening out at infinity?
I mean, if it's outside your window, then I don't care. So as long as I can I have a way to home in on anything that's inside my view window, I can forget.
So we should like choose a window. Yeah, I think we kind of have to, there are multiple techniques to doing this, and I'm not going to talk about one of them, but I'm going to focus on this windowing technique. I should choose a view window, but I don't want to choose a view window before I've done any work, because then like, what if I choose a little tiny view window and like now I'm dead in the water, right?
Otherwise,
Or you're done.
Or you could be done. Maybe it's actually really pleasant. Maybe all the solutions I cared about were just really near the origin. I don't care what's happening. I've done some actual computations where that's been the case. Where like we just choose a little view window and it's all good. I don't care what's happening out there. But in this case, I want to know. I really want to know what's happening out here. So view window. Is there a sensible way to take the view window? We have these points at this point.
Include all those points in the view window.
Okay, let's include all those points in the view window. Okay, so should I go like this
And a little extra buffer.
and a little extra buffer? Okay, so let's push out just a little bit right here.
Maybe twice as
do
much.
some probability testing on the points, right? Move in different directions, parameterize it.
That seems really scary to me because these points are singular. So I think moving these points is going to be a real challenge. We could practice deflation and do it, and my algorithm does that, but I don't want to do that right. This is far too early to be playing games with deflating singular points so that I can make them trackable. I don't want to do that. That's way too heavy. The rectangle we have is decent.
Oh, sorry, I was going to say, I suppose you could have a problem if there's happens to be some component that has no critical points on it for a particular projection.
Yeah.
It's going to sort of hide, but how easy is it for that to happen? Would we have to get lucky, very unlucky?
It's not that hard. If I just have a line.
Yeah.
Yeah, my software, in fact, I have C++
yeah.
software and my software misses lines.
Yeah. And I see, and if the line is, even if the line is wiggly, it'll still miss it. As long as it's not wiggly enough to go critical.
Yeah.
Sine curve.
Okay,
something like
so
that.
you might, I guess, want to take this whole procedure we're about to describe and redo it for a bunch of different directions.
That would certainly be helpful.
Okay.
I'm just thinking about how to deal with the infinity right now. So let's
Okay.
put that on ice. Let's just think about infinity. I don't really like this because now I have to go like slice to the left, slice to the right. So I have to go twice for each axis that I have here, right? Which is fine. I could do that. I only have 2 axes here, so I only have to like cut 4 times in order to do this. But I'd really rather just cut once. I'm a mathematician, right? I invent tools so I can be lazy.
You can even port it to a sphere.
Oh, yeah, I like the sphere idea. Why don't I take the centroid of this object? I think that's the canonical symbol for centroid, or maybe rotate 90 degrees and I get it. So I'm going to compute the centroid of these things, and now I'm going to take the radius to the one that's furthest out. So we'll let that be the radius to the furthest, our max. And then choose your favorite number that's bigger than 1, and we'll get a circle that's bigger than that. Okay, and now I'll intersect, and I will find 2 points out here, and I'm going to draw those as double dots because they're reminiscent of the lemma set for infinity. Yeah, okay, so now we've dealt with infinity. So that's what I do on step 2 over here, and I will have star, star, regular point, double dot, and I have that collection of points. Okay, so we're getting closer. We're getting closer. I have my line, and I have.
Can I back up? for a minute?
Please.
So you said, okay, so the stars are the critical points.
These are my critical points.
Then from the critical points, you
They're
created
singular,
a few.
Sorry, these are singular points. I have singular points,
Oh,
regular critical points,
okay.
and
Okay.
infinite
Got it.
points.
Thank you.
Yeah. Or sphere intersection
Yeah.
points.
Did we do something to detect singular points or?
I get them
Yeah.
naturally from having
That-
solved this expression
okay.
over here.
Yeah,
Yeah, they'll pop up because this determinant is 0 trivially for
Yes.
for any of them because this thing will drop rank.
Yes.
Yeah.
Okay.
Mhm. Yeah. Okay, so I've computed this set of points out here, this set of 6 points. Feeling pretty good, but I haven't quite gotten to the point that I have a curve. You know, it doesn't look like a curve. This to me looks like a collection of points. So on my next step, then I think I'm off a step. I was supposed to replicate and draw it over here. So I'm gonna go to infinity. This is gonna be step 3. I diverged from my plan. All right. So step 3 is now I want to start getting to the point that I have additional data beyond my critical points. It's not enough to know the critical points. I want something that looks like a curve. I think of this as my slice. We're going to slice and dice because I know that all the interesting stuff happens at these places. Each one of these things is a p value that I get from projecting in the direction of my pi of x, y, and they're all distinct from each other. And they're all distinct from each other because I used a random copy of a line right here. So we're not going to choose to use any particular line. My software will let you at your own peril, but it will just randomly choose a line to work on. Okay, so I know all of the interesting stuff happens at these places. And I know between these places, nothing interesting happens. Or rather, maybe that's just like, it's pretty normal in there. So what I'm going to do is I'm going to cut at each one of these places. I'm just going to take each adjacent pair of these. There's some numerical problems here we should be concerned about. And then I'm going to go upstairs and I'm just going to solve. I'm going to solve this polynomial system that says that the projection value is equal to this. And we'll find a point that lives on this piece of that vertical line. That's one of the 2 components in the solution system. We'll find that point.
Or there might be a couple, or just there's only one.
Well, in this case, I just happen to have 1 because we're above the circle, right?
Okay.
This is the oneness, right? Now we'll know 1. We finally know 1. There is 1 point above us. If we're looking up in that direction, that's up for me. I'm looking up and I know the number is 1. And I know that between these 2 critical points, it's always 1. Always. The only places it can change are out there, but we know that that was off to infinity, so nothing interesting happens. And down here, I know that something happens, and let's find out. We'll cut, and I will find boop, boop, boop. I'll find those points. And now I know the number is 3. And we're just going to cut between each one of these places. So I'm going to go up here. I'm going to find a place there, a place there, and a place there.
It's still 3.
The number is still 3. We're gonna find another 3 right here because we're gonna be on, let's see here. Oh, yeah, we'll find one on that handle. We'll find 2 on that right-hand side. And then down here, I'm gonna find 1 that lives on my handle. Okay. So we're pretty much there. We're really starting to figure it out. And if I go and erase these lines, it starts to look an awful lot like a circle, or at least you can start to see the details of it. But like, I'm still dissatisfied because all I've done is compute some points, some special points and some generic points. I don't have a curve yet. I just have points. So what I'm gonna do then is, so 3 slice, I'm gonna be a DJ for a little bit. You know, you can like fade between, if you have 2 turntables spin it, they spin in the same direction. As a fader, a slider you can use to fade between the 2 things. I'm gonna be a DJ. I'm just gonna see what happens here. So I'm gonna take and just replicate like one of these bits down here. And this is what I'm gonna call as connect the dots. There's a function in my software that is literally called connect the dots. I like to have fun with my software. So I will have, let's do it for like this piece right here. So I'm gonna do that down here. So I have a singular point.
Using splines or something else?
No, straight line segments. And then I have a cut, and then I have a critical point. And I have down here that this midpoint lives in between my singular point and my critical point, but I don't distinguish between those usefully at this point. I have that information, but it's not needed. So I'm gonna form a dial right here. There's my DJ slider that I can move right and left. So if I just always force this to have a certain projection value, namely the value down here, which would be called like, say, like M or something like that. And these ones right here, I'm gonna call P sub L and P sub R. I just need to deform M to P sub L and M to P sub R, L for left, R for right. And I can do this by forming the following system. I'm gonna go F of X, Y. That keeps my point on my curve. Cool. And then I need to go M times, I better refer to my notes to get this right. Okay. Start over with that one. I'm gonna go pi sub X times X plus pi sub Y times Y minus something equals 0. See if I'm still on the screen here. So right here, I'm going to introduce a number, which I'm going to call T. And I'm going to take T times M plus 1 minus T times P sub, say, L, if we're going to move to the left right here. So I'm just going to do one direction at a time. So I have a number that lets me move between these 2 spaces right here. T equals 1 is when I'm at M, and T equals 0 is when I'm at the left. So I'm just going to start right here. I have a dial or a slider. I've got like a laser pointer that points up, and what we're going to see is that this point tracks to these 2 points. So I get graph theoretic information. I know that this point here connects to that point right there. So now we've established the connection. Yeah, now we've established the connection. And if we do that up here on my full diagram right here, we will find connections that look like this. And this is why I called my talk today Skeletons of Algebraic Curves, because like I feel like I look on the outside nice and smooth and soft and squishy, but like if we just look at the structure of this thing algebraically, it's pretty blocky. It's pretty blocky. This is what a circle looks like to me. And if you want more points on this thing in what I think of as step 5, that's going to be to smooth the object.
Are you testing just 2 values of T in that one, or are you?
It's a
putting
continuous,
lots
it's a continuous parameter.
of- This I know, but like, you're not gonna try every single value of T in there, of course, because there's a lot. Are you just like doing two of them to see what it connects to, or what do you?
Yeah,
actually
I only
do?
have to move it from 1 to 0 as I move from the projection value in the middle to the projection value on the left, and I'll establish the connection.
Well, why don't you
I'll-
just say, I'm plugging in the projection value on the left? It's like a complicated way of saying that.
Because if I just solve this expression when t equals 0, then I won't have seen this, and all I'll do is compute this point again.
Yeah,
That's not helpful. I need to know from this starting point that it goes here. I need to know in terms of this bigger picture out here, that when I track this point down here from left to right, that it doesn't like jump and do something like that.
Ah,
This example is simple, so we're not gonna see that, but yeah, I need to know. I need to establish the connection.
So do you choose like a large number of values for t to track the movement of the point?
Well, all I care about is finding the connection, so I'll just track from 1 to 0.
but like either you just test one and just test zero, which you said you didn't do, or you do a lot of values, which you said you didn't do. Like how do you determine what happens in between?
For each midpoint that I have as crosses in this, I track it to the left and to the right, and I just like see where it goes. And for these ones right here, maybe you're concerned with these ones right here because there's not critical points in between these. So what I've drawn on here is a lie. We do that a lot as mathematicians. As I'll discover like new points that map between these, where like they're in like the fiber of the projection value. I don't think I've addressed your question though. Like
Do you,
what?
like, does t equal 0, 0.1, 0.2, 0.3, 0.4?
I can do that, and if I do that, I'll establish a set of samples that look like this. But for me, it's enough to have a single point in the middle. And then if you want more points, I can just slide my t dial to the right or to the left and generate additional points to the right or to the left as I wish.
So you plug in t equals 1/2.
T equals 1/2. Well, so depending on how you phrase the system, I would think of t equals 1/2 as being right in the middle.
Okay.
And then 1 goes to the left, 0 goes to the left, and 1 goes to the right, maybe. There are various ways to do it and think about it.
You have some mechanism of solving that system of equations.
I do, yeah.
Buchberger's algorithm or something like that.
Well, Buchberger is for doing symbolic work, and this is pure numeric work.
Right.
Also, Buchberger works over the complex numbers.
enough.
And so, yeah, we're in the world of numerics right now. Yeah.
So, okay, so I don't want to derail the talk too much if there's more to it, but I did.
What about at the end?
If there's, okay, for at the end, I don't understand why the equation that you wrote creates an interpolation between adjacent critical points.
This right here that I wrote down creates an
Right.
interpolation between a midpoint and the critical point to the right or to the left.
Ah, okay, I see. So I missed this step, I guess, which was, so you have your critical points.
Mhm.
Was that the slice step? You also get midpoints?
Slices to get midpoints.
Ah, yes.
Yeah, so 1 is critical points. Step 2 is infinity, which gives me my stuff that's above and below down here.
Right.
Step 3 gives me my midpoints, which are generic points in the middle of my arcs. Step 4, I do connect the dots where I establish that these 2 points are connected to each other. This midpoint tracks to this one. And if I were to go further, I would try to cross a singularity for this expression, and I better not do that. So I can't go further to the left or to the right. I
Okay.
can't. Maybe I can for some of them, but like for most of them, I can't.
So I think, okay, I think then that was my question. So you have this new system.
Mhm.
T is now, you said you choose a value for t, or t is
Yeah, it's a
variable?
dial I can do. There's an ordinary differential equation. These are all essentially just constants. There's an ODE and T that I can solve using ODE methods
I
to
see,
track
okay.
left and right. There's a
I see,
homotopy.
okay.
This is a homotopy.
Oh.
If that language is acceptable
Yeah.
to you. Yeah, I have a
Oh.
homotopy between those two things. I can
Okay.
continuously deform them.
So, okay, I think my question then is just, yeah, why does that thing interpolate between the midpoint and whatever connected critical, or maybe that's the wrong question.
But-
Is there a well-defined thing where it's like this thing, if you solve this equation, you'll definitely get that? Or is this kind of a heuristic where it's like,
I'll definitely get it because it's algebraic.
okay,
There's an additional piece of information that this by itself doesn't define these things. It's this plus the fact that I started at this point,
Yeah.
right? Because like in the world of ODEs, your start point's important,
okay,
right? If you have the same ODE and you solve it from different start points, you'll get different
Yeah.
solutions. The start point is that midpoint.
okay. So the thing you said, okay, let me back up and see if I can. do it. So you said,
Mhm.
because we're in between the critical points,
Mhm.
we know that there's not necessarily like one sort of how do I say, one value at each thing, but at least the number of values doesn't change.
Yeah, that's right.
So, okay,
Uh-huh.
if that's what you said before.
Yeah.
So you know you can do some sort of, if you sort of look upward, as you said, you'll see a bunch of segments connecting the critical points to each other, and maybe they'll merge at the critical points, but
Yes.
they won't merge in between.
Yes.
And then so you said you find the midpoints. However many you find, you know that has to be the number of segments, and there's one on each segment.
Yes.
So yeah, I guess my question is, yeah, why is it that that equation, solving, let's say that ODE, gives you the segments?
Well, I will solve it once for each midpoint that lives in this fiber.
Right.
So I'll run this process once for each midpoint, and we'll find that like two of them connect. Now I'm not talking about this sphere example anymore, but I'll do this in principle once for each. In practice, I'll do them all at once because the algorithm will
Right.
do
Yeah.
as many start points as I have for the ODE and solve them. And then I just have to like look and map them.
Let me
Hopefully
put
we
it
can get
a
out.
different way. It seems clear to me that the points that you're getting out of this,
Mhm.
oh, I guess they do have to be, okay, they have to be on the curve because of the first line.
Yes, this is the thing that requires they're on the curve. This is the action that makes it move to the left or to the right.
What's the specialty
Oh.
about the midpoint? Is that?
Nothing.
Okay.
In other words, this is an equation. Can I think of this as an arbitrary equation which you've written down?
I think of this
With
as a
the-
controller. I think of this
Well-
as a slider such that I can slide this, and sliding this dial right here adjusts the value in T right here. And
Can I-
sliding this is taking the action of solving an ODE.
Can I think of it as an arbitrary adjustable equation with the property that the midpoint is a solution to it when
Yes.
T is at 1/2,
Yes,
and the endpoint critical points are solutions when T is 1 or -1 respectively?
yeah,
Or sorry,
if you want it
1
to
and
be,
0
if you want it to be 1/2 in the middle, then I will go piece of R right here.
Sure. Or
So
yeah,
now
either
0
way.
is over here,
Yes.
1 is over here, and now
Sorry.
1/2 is in the middle.
Yes.
And I'll start it at 1/2 now.
Okay.
We have our choice, we have choice.
And so the idea is you could have written any equation that has those three properties, and that
Yeah.
also would have worked.
Yeah, but this is what's called the
Okay.
straight line homotopy. We're just gonna walk on the straight
Oh.
line between them, and it's straight line and T, but we don't have to take, we could do T squared if we wanted.
Well,
It's your choice.
I mean, to be clear, it feels like it's not a straight line in the plane, right? Like
That's
in-
correct.
In the plane, it's actually because of the
That's
F
right.
line, it's actually
Yeah.
tracking the curve.
It's a straight line in T. But it's not a straight line,
Uh-huh.
it's not a straight line in the space that we're tracking in. Yeah,
When you're picking the points at infinity, on the circle, do you have to pick ones that are gonna be like on the very left and the very right of the line, or do you just pick them arbitrarily?
well, so the way I'm gonna get my points at infinity is by just taking the center, like the average of the critical points, the singular points that I have. I'm just gonna get this point in the center. I'll find this distance here and then just like choose some radius that's larger than it. And you'll find the stuff that's interesting inside of it. So they're kind of arbitrary points that are outside of the circle containing these objects.
Yeah, but you have two, so the circle, like you're choosing 2 points on that circle. And so the way you choose them is trivial, like you don't, or do you want them to be like on the very left and on the very right of that line so that it kind of.
Okay. So once I get these points at the top and the bottom, right? And why do they show at the top and the bottom is because the thing that I'm working on here is the circle with a line, and this line goes to infinity. So the points that I have at the top and bottom here are the intersection of my infinite line. I've got this infinite vertical line. They're the intersection of this vertical line. So if I had a horizontal line by, say, multiplying by y here instead of x, then it would have gotten 2 points out here instead of those vertical ones. So they're just whatever they happen to be, the intersection of my object with a large circle or sphere. So they're not special antipodal points. These are the intersection of my algebraic curve. I just don't know what my curve is at this point in the algorithm.
So
All I can compute is points. It's all I can ever compute is points. So what does it mean to me? Let's bring this to a close because it's been lively and fun, but it's time for lunch, I think. What does it mean to compute a curve? For me, it's to compute a union of points, of critical points where I know that behavior changes, and of middle points where I know that everything's all good. It's nice and smooth and there's nothing changing nearby, with a graph of connections between them such that I can exploit that graph to compute additional points if I want. So that if I want something that looks smooth, I can do that. But if I'm content with something that looks rather skeletal, I can do that. I think I
All
will
right.
stop
Thank
there
you.
and say thank you so much.
More questions?
Happy to entertain more questions.
Can you explain again, what is the 13331? Yeah, a little bit
Hmm.
confused about that.
Let me, well, how much do I want to refer to that later? I think I don't want to refer to this one any longer, so I think I'll let that one go. So the question was, what did a 13331 refer to in this diagram? So let's draw my curve. My curve is a circle that has an infinite vertical line on it. I have randomly chosen a diagonal line to decompose it. And then if I shoot lines, if I'm like always looking up from the object in this direction.
Oh, you mean how many intersection points?
Yes.
Oh, okay.
So here it's 1. And if I take and sweep this line to this direction, there's a point here where it's going to suddenly jump to 3 in between this band right here. And then in between here, all the way until I get to this point. I'm
Okay,
going to
okay,
have 3 points
I see.
and then another 3 and then 1 forever from the other
Yeah,
direction.
I see.
Yeah.
And you mentioned the slice to get midpoint, but the midpoint is just a generic, it's not a special, critical, or singularity.
Exactly. The algorithm has been constructed specifically so that when I do that slice, there's nothing special about them. Why do I need there to be something special about them? Well, when I do my homotopy left and right, when I do this left and right action with this straight line homotopy I've constructed here, I'm solving an ODE. And if I try to solve an ODE at one of the branch points, we'll never get started or we'll get unexpected results because I'm starting solving an ODE from a singular point in that solution space, which I better not do. So I can only start doing this process from a generic point or something to be really not special. It needs to be nice and smooth. And the algorithm is constructed so that where would this fail? Where can I not track away from a start point in this action? At these critical points, at the singular points? We could at the sphere, but somehow I need to deal with these things. This set of points that I get from steps 1 and 2, critical points and the infinite step, are precisely the places where this will stop. So after I cut and my slice and get the midpoint step, everything that I compute in this step is going to be a nice smooth solution for doing the tracking in this homotopy step to solve this ODE. It's precisely that there's nothing special about them. That's why I computed them.
But how do you decide the first step? How do you decide the circle radius? Where you just choose a randomly enough large one?
In the software, it's the number is 3. I take this distance, the distance from the centroid to the furthest, and multiply it by 3 because 3 was a good number.
Okay. And do you differentiate to critical and singular point, or do they all call critical point?
I kind of flatten them all into critical points at some point, but I do retain meta information about them. So I can distinguish. In this algorithm, it's not useful to distinguish between them. But if you wanted to do additional computation beyond this, like say I do this for surfaces, which I can do, then I should know which ones are singular and which ones are just plain critical. Because the critical points are the ones where if I just chosen a different line, right? If I just rotated this, then my 2 critical points would have just been, they're actually not special either.
Right. Depending on which P you're choosing.
Exactly.
How do you choose the line onto which you project?
Random number generator. Or you can type it into a text file and feed it into my software and tell me which line you'd like to choose. But you better not choose the horizontal line, because if you choose the horizontal line, then this entire vertical component collapses onto one point and I can't possibly compute it.
So how do you know that, like, how do you know how to avoid those? Like if your vertical line was at a different slope than
The set of bad lines is a set of measure 0. And so we have faith in the random number generator.
okay.
There's some deep results in algebraic geometry that I don't know how to cite by name at this point that let me know that if I just choose random numbers, this will work. In practice, watch out for sets of measure 0 in the world of computation, because it turns out that the floating point numbers, which we use to represent continuous spaces, are in fact themselves discrete. And so the probability is not 0. And if you choose something that's almost horizontal, the algorithm will struggle because now condition numbers went up and the software is going to behave poorly. So I'll be honest with you, my software for computing curves, pretty reliable. For surfaces, it's got some issues. And those come from the question that Daria just asked, how do we choose the random numbers? I don't have any way to, Daria. I don't. I'm dead in the water. But I get pretty good results. Most of the time.
Just run it, if it doesn't work, just run it again and it'll do a
Yeah.
different random number.
Yeah, dial some precisions down, tighten some tolerances, run it again.
Surely you can't hit a set of measure 0 3 times.
Oh, if
Well,
only.
the floating
What's-
point numbers themselves are a set of measure zero. So you're
Yeah,
sort of out of luck there.
it's really scary. I could go on at length about like
Yeah.
ways of dealing with this. Well, we dealt with many of them, but it's all challenging.
Could I take another stab at what this slider is doing?
Yeah, let's do that and then
Can
let's
we
go
do
to
it
lunch.
after, wait, can we ask, any more questions before that? All right, let's thank Sylvia
Okay.
again, and then we'll
Okay.
have more questions.
Okay,
Thank you.
thank you.
All right, go for it, Aaron.
One more question, and then I'm going to lunch. Aaron.
Okay, so tell me if this is. Not expecting that.